Well, let's have a look at some problems where we apply this formula. Exponential functions, obviously it's going to be really useful for exponential functions. So there it is, but I've just added a little bit on there. The plus 2i k pi. Basically it's saying, well, the argument is a certain angle. It's the principal argument, but of course, you go around the circle 360 degrees or 2 pi, you're going to be back in the same spot. So the actual power would give you the same answer. It's just not the principal argument. So they will be the same so long as k is an integer, of course, because you need multiples of 2 pi. You need to go around the circle completely. But they will be the same thing. They will produce the same answer. So e to the I theta plus 2 pi k is the same as e to the iota theta. What that basically means is it's a periodic function, just like the trig functions are. Every 2 pi, or 2 pi I, every 2 pi I, this function will repeat. So our trig functions, trig identities now. We've got another way of playing with trig identities. Remember these ones we did the other day, really useful. Z to the power of n plus 1 on z to the n is 2 cos n theta, and then a similar one for sine. Okay. If I rearrange those, I can make cos n theta the subject, and I'll end up with a half e to the n theta I plus e to the minus n theta I. And sine n theta, we rewrite that one, we'll get 1 on 2i e to the n theta I minus e to the minus n theta I. So now let's prove this very simple trig identity. Sine squared plus cos squared is equal to 1. Let's prove it to be true. If I substitute in for sine and cosine now, but of course I'm squaring them. Okay, well there's a common factor of 1 on 2 squared there, so I'll pull that out. There's a quarter. Expanding out, but not forgetting the I squared, I've got to take that into account. I'll end up with this expression, minus e to the 2i theta plus 2 minus e to the minus 2i theta plus e to the 2i theta plus 2. All those exponentials end up cancelling. A quarter of 4 is 1. Bingo, we got the answer. How about something interesting like this one? Sine cubed theta is 3/4 of sine theta minus 1/4 of sine 3 theta. Okay? Well, sine cubed theta would now be e to the iota theta minus e to the minus iota theta over 2i to the power of 3. Expanding the top out, and 2i cubed, of course, would be minus 8i. So there's sine cubed theta. I'm just going to factorise this. But again, a clever factorisation where I'm factoring the coefficients together. So the 3's and the 1's. And when you look at that, then you can see we've got 3/4 of sine theta minus 1/4 of sine 3 theta. There's the proof of that little identity. What about this one? Products to sums. I know we love this one. Let's prove it. 2 sine alpha cos beta will become this expression. Okay. 2's will cancel, so my denominator is 2i. Expanding the top out, but expanding the top now becomes quite easy because exponentials, we just add the powers. And we end up with that. Well, hang on. Again, I'm going to split this up. And this time I'm grouping the things with the same, well, not exactly the same power. One's minus, one's plus. But you can see one group's got alpha plus beta, one group's got alpha minus beta, because that now means we've got sine of alpha plus beta plus sine of alpha minus beta. Finding roots of complex numbers then. Yet another way of finding the square root of a number. So 1 minus the square root of 3i. Well, so we're saying z squared is 1 minus root 3i, but now I'll put that into exponential form. So it's 2e to the minus I pi on 3. Therefore, z will be the square root of 2. Notice now I've added in the 2 pi k, because I need to create more than one solution. K equals 0 and 1. Again, I just need 2 consecutive numbers. Remember, e to the power of z is the same as e to the power of z plus 2i pi k. And there's my 2 answers in exponential form. Convert back. There's our answer. Don't know that I actually do it that way, to be honest. I don't think that's the best way of finding the square root of a complex number, but it is another way you could find the square root of a complex number. Let's have a look at the past couple of years HSC. What sort of things do they ask? Question 9, so of course it was actually a multiple choice question, but they asked this one. What is the maximum value of this expression? 0 is in between 0 and 2 pi. Now, of course, people fall back to algebra. They go, oh, let's do this via algebra. But there's a beautiful way of doing it geometrically if you think about what this is actually saying. If z is a complex number, our complex number is e to the iota theta. Its modulus is 1. So z lies on the unit circle. So there it is. Z is e to the iota theta. Any z will find itself on that unit circle. But what is the question now saying? Well, the modulus of z minus 2 we know is the length of the vector that joins z to 2. There's an example of one of them. Remember, it could be any point on the circle. Modulus of z plus 2 would be the length of the vector joining z to negative 2. Now, it's got to go to the same point because whilst I can pick any random point, they've got to go to the same point. Now we're saying, what's the maximum value? So in other words, where do I place z so that the length of those two blue lines is a maximum? Now, of course, I've placed it in the right spot straight away because you put it anywhere else, one of those is going to shorten, the other one's going to lengthen, but it's not going to give you the maximum. I mean, the other spot I could have put it would have been down at -1, because obviously that would give me the same length. So it's when z is plus or minus I. Okay, well if z is plus or minus I, let's find the length of that vector. What would the modulus of I minus 2 be? It would be the square root of 5. There's our maximum, 2 root 5, because they're both going to have the same length. Great question. It was, as I say, it was multiple choice. But yeah, it would have been a good question even if it wasn't. 2021 paper. By using part I or otherwise, show this expression. Now, I haven't bothered putting part I in. In part I, simply had to prove this relationship. So that sort of question. Cos 5 theta was 16 cos to the power of 5 and so on. So you've gone and done that in part I. You now have that relationship. When they say by using or otherwise, use it. Like, sure, you can go do whatever you like, but they're kind of giving you a big hint here that this is probably the best way of approaching the question. So the real part of e to the I pi on 10. Well, e to the I pi on 10 would be cos plus I sine, but we just want the real part. So it's the cosine of pi on 10. So this question is now essentially asking us to show that the cosine of pi on 10 is the square root of 5 plus root 5 on 8. That's essentially what we're now trying to do. So if I let theta equal pi on 10 in this relationship that we used in part I. So everywhere I see theta, I'm replacing it with pi on 10. Cos 5 theta becomes cos pi on 2, which is 0. So I now have cos, or 16 cos power of 5 pi on 10, etc., is equal to 0. So all of that came from part I. And look, it is a show that question, so I should really be explaining where I'm pulling information from. So right-hand side of my paper, that's what I keep it for. Explanations, things like that, I'd put, okay, I've got this from part I. Also highlighting the fact that I've done what you actually asked. I used part I. Let x equal cos of pi on 10 for this particular equation that I've now created. Not a coincidence, it happens to match what I know up above. So I already know it's a solution. So cos of pi on 10 has to be a solution to this equation. Well, I'm going to divide everything by x, and I can do that because I know x is not equal to 0. Because we said x is the cos of pi on 10. No way it could equal 0. So it's perfectly valid to divide by it. Again, explain why I can do that. X can't equal 0. We know that. X is cos pi on 10. Okay, I just now solve this equation and I must get the solutions. One of those solutions will be cos pi on 10. So x squared is 5 plus or minus root 5 over 8. Therefore, cos pi on 10 is equal to, well, I've got 4 possibilities. I've already got rid of one, you might have noticed, because it would have been plus or minus the square root of 5 plus or minus the square root of 5 on 8. I know cos pi on 10 is going to be positive, so I didn't even bother considering the negative square roots. Okay? Pi on 10 is acute. Cos pi on 10 therefore has to be greater than 0. Again, explain why I got rid of it. I can't just magically get rid of it, especially in a show that question. Because in a show that question, they could accuse you of going, well, you knew what the answer had to be. Did you really know why you made that positive? Or did you just get rid of it because it had to so you could get the answer? It's either going to be one of these two things. I've just done an approximation there to get a feel for what my two possibilities are. I've got 0.59 or 0.95. Kind of nice little symmetry there, by the way. Let's look at the graph. There's the cosine function. Now, cos pi on 10 must be bigger than cos pi on 4. Cos pi on 4 is 0.71. So I know it has to be bigger than 0.71. Well, now I know which one of the answers I need. It's got to be the 0.95 solution, which would be the 5 plus the square root of 5. Thus, there's the real part. Okay, 3E.